Today we want to take our specific heat calculations one step farther into something useful, and that is by using a process called calorimetry. So you probably already watched the video I suggested to you about the theory of this, but this is how I did it in my lab. I have pictures left over from our lab last year. We would use this equipment here, all stuffed in a bin, and if it's spread out, you would need to determine the mass of that of your sample. We would heat up our sample in some water, and we could measure the temperature of that water right there to monitor the temperature of the sample. And then we take that sample and then drop it in a coffee cup that is also full of water, and we noted the temperature of this water before, and then we know, and the water will heat up. Duh, right? Because it got hot metal put into it. And the temperature would rise, and we would record the final temperature. So we have an initial and a final temperature. All right. So and that's all the extra equipment you really need. It's a very simple experiment. But view is very nice to see too. So if we were just to make sure you understand, if you can do this calculation and get this answer, you are good to go for this experiment. Now, I'm not worried about your algebraic skills in this thing. I really want you guys to really understand the process of how you be able to do that. So what I just explained is the most important part. So calorimetry is the process of determining the heat of a reaction, is a branch of chemistry called calorimetry. The basis for calorimetry is the first law of thermodynamics, also called the law of conservation of energy. The apparatus is called the calorimeter. Now here we have a bomb calorimeter. This is an actual one that you would use in a lab. You can see right here, and then they would submerge it into the chamber right here, and then they would start it. You don't ever actually get to see anything, and it doesn't explode, even though it's called a bomb calorimeter. And then you have the coffee cup calorimeter, which works pretty good, but as you can tell, it's not going to be perfect. So the ideal setup is going to look like this. This is a diagram of it, in case you are bored and want to really check it out. So the calculations are going to work out this way, where a sample of iron having a mass of 93.3 grams is heated to 65.58 degrees Celsius, is placed in 75.0 grams of water, raising the temperature from 16.95 degrees Celsius to 22.24 degrees Celsius. Find the specific heat capacity for this iron sample. If you don't want me reading these, remember you can skip ahead. So what we were going to do is, remember, we have water and we have iron right here, and there are two different substances. So now what is going to happen is the iron is hot. It's been heated up to a high temperature, and it is going to be placed into the water. So the heat is going to go out of the water. We will notate this algebraically by putting a negative sign here, because the heat is leaving the iron and going into the water. It's important to understand that, because this is a conservation of energy. The heat cannot be destroyed, right? It has to go from here to here, all of the heat. We're just going to assume that. So, well, we know that Q is MCAT, so we're going to substitute MCAT for Q, right? So now we have all of our values here. So we have the mass of water, specific heat of water, change in temperature of water, the mass of iron, the specific heat of iron, and the change in temperature of iron. We'll glean all these this information and put it into our sample right here. So we have the mass of water was 75 grams. That was easy. The specific heat was not given here, but I already know it. It's one of those numbers you kind of know always, because we use it so much. 4.18. And the change in the temperature of water is final minus initial. It was final minus initial. So that's no problem there. And then we have the mass of iron. No problem. That was given to us in the problem. And then the specific heat of iron is what we're looking for, right? And then this one right here is the toughest one to get. What happened with the iron is it started out at this temperature. It started at 65.58 degrees Celsius, and it cooled down. But what did it cool down to? It wasn't given up here. Well, you have to logically, intuitively assume that it cooled down to the same temperature as the water. So it cooled down to 22.24. the same as this water right here. So this is the final temperature of the iron, okay? And also the final temperature of the water. They are the same, okay? That is the key difference here. Now notice that this one will be negative, which conveniently will take care of this negative right here. So what I'll do is I'll compact everything on the left side, and then I'll compact everything on the right side, and then just solve for the specific heat of iron. Simple enough, right? Well, it was 0.410 joules per grams degree Celsius when I measured it in my experiment. But if I look on here, I get it's 0.449. Close, but not exact. But why is that? Well, remember that your iron, we assume that the iron was pure. We assume that the water was pure. And we also assume that the specific heat was 4.18. The heat, we assume that there was heat loss, that there was no heat loss of the surroundings, but there will always be some kind of heat loss of the surroundings. That's actually the second law of thermodynamics. And then we also assume that 100% of the heat from the iron was transferred to the water. So lots of different assumptions and reasons for error. By the way, you can take this as your actual value right here, and you can take this as your experimental value and find a percent yield from that. Very cool. That would be a nice investigation. So for example number 6, what is the resulting temperature when 35 grams of water at 75 degrees Celsius is mixed with 15 grams of water at 15 degrees Celsius? Well, we have cold water and hot water. Again, the heat will leave the hot water and go into the cold water, right? We're going to assume that they're the same. So we'll assume that MCAT equals MCAT, negative MCAT. And we will have our cold water is 35, our specific heat was 4.18, and this is 4.18, and this is a final minus initial, and then our final minus initial. Now those final temperatures are assumed to be the same, and that's going to be the key here. It looks like there's 2 variables, but there's really only one. So we just need to algebraically solve for this. Well, we'll just cancel out that 4.18 and get that out of there, because that's the same on both sides. And we're going to distribute both sides now, and we're going to get 35. We're going to distribute this. We're going to distribute this. And then we're going to isolate TF, and we're going to get that over on the left side. We're going to get all of our constants over on the right side. And then we are going to shrink it down and then solve for TF. Very simple. Now that makes sense, right? 33 degrees Celsius. It started out at 15, and then this one started out at 75. But because we had 2 different masses right here, they're not going to meet exactly in between 15 and 75. They're going to meet somewhere about 33. So that does make sense. Now another thing you can do is when a 16.9 gram sample of sodium hydroxide dissolves in 70.0 grams of water in a calorimeter, the temperature rises from 22.4 degrees Celsius to 86.6 degrees Celsius. Calculate the heat produced per mole of NaOH for the process. Unfortunately, I just realized that I just produced the heat, not the heat per mole, but that's okay. So the reaction here is just this breaking apart, and since we are breaking these bonds, and these bonds are going to form with water, this is the chemical reaction that's going on. The Na plus is going to bond with the sodium hydroxide, remember our solutions unit, and that forming of those bonds is actually going to be releasing heat. And this releases quite a bit of heat, okay? So much so that it's actually 23.3 kilojoules. Let me walk you through what we did here. This mass right here, we had Q equals MCAT. The mass is going to be the mass of the sodium hydroxide and the mass of the water. We're going to add those together, and we are going to assume that the whole thing still has the same specific heat. It doesn't, but we're just going to assume it just for practical, just for this. And we are going to, and the change in temperature is this. We will find our heat. Now what we should do is divide by the number of moles there to find the heat per mole, but I'll show you that in the next example. So the heat released from the combustion of a 0.0500 gram of white phosphorus increases the temperature of 150 grams of water from 25.0 degrees Celsius to 31.5 degrees Celsius. Calculate a value for the enthalpy change, kilojoules per mole of combustion of phosphorus. The specific heat capacity of water is 4.18 joules per gram degrees Celsius. Okay, so the hint right here is that the enthalpy change is just the heat divided by moles. Like, that's a fancy word of saying that. I don't know why we always try to make things more complicated. So seriously, what you got to do is you really just need to determine the heat by taking your mass of the water. We're not going to add this time because we just burn the white phosphorus underneath the water. That's all we're doing. So we're just going to take the mass of the water and the specific heat of the water and the change in temperature, okay, and find out that it is kind of a lot of heat, 19.7 kilojoules. Now then we need to divide it by the number of moles. So to find the number of moles, we just take the grams of phosphorus and divide it by its molar mass and find the number of moles. That's easy enough. You learn how to do that. And then we just have to take the kilojoules of heat and then divide it by the number of moles. And we get an insanely high kilojoules per mole, or enthalpy, right here. This is quite large, but remember, the white phosphorus is quite hot, all right, when it burns. So hot that that's what they use in military grenades. It is one of the hottest things to man, and it's pretty crazy. So that's going to be it for calorimetry, you guys. Don't worry too much about the algebra. I really just want y'all to understand the process. All right, have a great day.